Hello, welcome. In this short video, let us look at an example illustrating on how to evaluate the different statistics of derived random variables from a given joint probability mass function. So, given the following joint probability mass function, P of probability, that is P of x comma y, defined as follows. That is for values of 1, 2, 3, and 4. This is for y-axis, and the values of 1, 2, 3, and 4 for the x. So the given probabilities are, the given values of the joint PMF are for 1 comma 1, that is for x equal to 1, y equal to 1, we have the PMF equal to 1 by 4. And similarly, for other values, we have 1 by 8, 1 by 8, 1 by 12, 1 by 12, 1 by 12, 1 by 16, 1 by 16, 1 by 16, and 1 by 16. So you can clearly see that for a given value of x, the probability of y, the random variable y, is uniformly distributed between 1 and the value of x. So this is the given joint probability mass function. Now our goal is to find out different statistics of the two random variables w and v, where w is defined as minimum of x comma y, and v is defined as max of x comma y. So the first goal is to find the expectation of the random variable w. So by definition, the expectation of any random variable is given by the summation over all values of this w, or this random variable, of the product of w and the probability mass function of this w. So this is the definition of an expectation of any random variable. So now we have to find the different values of w and also the probability mass function of w. So for a given function, that is minimum of x comma y, the range of w is given by SW equal to, obviously for the values of x and y with 1 equal to, or x equal to 1 to 4 and also y equal to 1 to 4, the possible values of w are 1, 2, 3, and 4. Because the minimum between 1 comma 1 is 1, 1 comma 2 is 1, and so on. And 2 comma 2 is 2, 2 comma 3 is 2, and similarly 3 comma 3, 3 comma 4 is 3, 4 comma 4 is 4. So thus the range consists of these 4 elements. So now we have the first part of this product. Next, we want to find the probability mass function for these different values of w. That is, for example, for w equal to 1, we want to find P of w equal to 1. So which is going to be, by definition, all the values of the sum of the values of this joint mass function at which the values of x comma y map to this value of w. That is, for example, here for w equal to 1, we have x equal to 1, y equal to 1 map to 1, and similarly x equal to 2, y equal to 1 map to 1, and all of these 4, and similarly the other two values also map to w equal to 1. So probability of w equal to 1 should be equal to the summation of x equal to 1 to 4, probability of y equal to 1, comma x equal to x, which is equal to sum of these 4 values. That is the probability mass function, the values of the probability mass function for a given value of y, that is y equal to 1, which is going to be the sum of these 4 values, which is 25 by 48. For w equal to 2, we want to find P of w equal to 2, which is going to be again x equal to 1 to 4, probability of y equal to 2, comma x equal to x. And this is equal to sum of the 4 values where the first value is 0. So this should be equal to 1 by 8 plus 1 by 12 plus 1 by 16, which is actually equal to 13 by 48. Similarly, for w equal to 3, we can find that P of w equal to 3 is equal to sum of these two values, which is 7 by 48. And finally, for w equal to 4, we have P of w equal to 4 is equal to the one value here, that is 1 by 16. Therefore, the probability mass function of w can be constructed as follows. For w equal to 1, we have 25 by 48. For w equal to 2, we have 13 by 48, and for W equal to 3 we have 7 by 48, and W equal to 4 we have 1 by 16. So you can verify the validity of this result by just adding up all these 4 values and see whether it equals 1. Clearly we can see that this equals to 1. So this is the probability mass function of the random variable W, which is defined as minimum of x comma y. Now that we have both the values of W and also this probability mass function, we can easily calculate the expected value as follows, which is equal to the first value of W is 1 multiplied by the probability mass function, and second value is 2 multiplied by 13 by 48 plus 3 times 7 by 48 and 4 times 1 by 16, which is equal to 7 by 4. Next we want to calculate the expectation of the random variable v, where v is equal to max of, that is the maximum of x comma y. Again, by looking at the xy plane of the probability mass function, we can clearly see that the range of the random variable v is also the same as the range of w, that is 1, 2, 3, 4. So v belongs to SV, that is equal to 1, 2, 3 and 4. So now we want to find the probability mass function of v, because the expectation of v is defined as summation of all values of v of the v times probability of v, that is probability mass function of v. So now we want to find this value, that is for v equal to 1 we want to find v probability of v equal to 1, which is again similar to the case for a minimum of x comma y. We want to calculate the probability mass function for a given value of v. So for example, for v equal to 1 we have, for v equal to 1 only the values of x equal to 1 and y equal to 1 map to 1. So the solution is 1 by 4. So it should be equal to probability of x equal to 1, y equal to 1, which is 1 by 4. Next, for v equal to 2, this probability of v equal to 2 is equal to probability of, is equal to for v equal to 2, that is we will get the value v equal to 2 for x equal to 2 and y equal to 2, and also for x equal to 2 and y equal to 1. So here the summation is across the values of y. So this is equal to, for y equal to 1 to 2, probability of x equal to 2 comma y equal to y, which is equal to 1 by 8 plus 1 by 8, which is 1 by 4. And similarly for v equal to 3, we have probability of v equal to 3 is equal to the probabilities of, for v equal to 3 we have the probabilities, that is for v equal to 3 we want to add up the probabilities along this line, that is for x equal to 3, because for these 3 points that we will get value of v equal to 3, because max of 3 comma 1 is 3, similarly 3 comma 2 is 3, and also 3 comma 3 is 3. So the summation is the probability of v equal to 3, which is 3 times 1 by 12 is equal to 1 by 4. And finally for v equal to 4, we have the last line in the xy plane, that is for x equal to 4 we have the for x equal to 4 and y equal to 1, 2, 3 and 4 we have v equal to 4. Therefore this is 4 times 1 by 16, which is equal to 1 by 4. So clearly we can see that probability of v equal to small v, that is the probability mass function of v, is equal to 1 by 4 for v equal to 1, 2, 3 and 4, 0 elsewhere. So this is the probability mass function of random variable v. Next we want to find the expectation of a random variable v, that is E of v. So from this definition we can easily determine the expectation as 1 times 1 by 4 plus 2 times 1 by 4 plus 3 times 1 by 4 plus 4 times 1 by 4, which is obviously equal to 10 by 4, that is equal to 5 by 2. Next we want to determine the variance of the random variable w, which is again defined as expected value of w square minus expected value of w whole square. We already know the expected value of w, so we want to find the expectation of w square, which is again from this definition here, which can be easily determined from this definition, that is w equal to 1, 2, 3, 4. We have the following probability mass function values. So from this definition or from this table we can easily calculate the required values for of the second moment, that is values of W square multiplied by the probability mass function from for W equal to 1 to 4, which is equal to 1 times, for W equal to 1 we have 25 by 48, so 25 by 48. For W equal to 2, that is 2 square, 4 times 13 by 48. And for W equal to 3, we have 9 times 7 by 48. And finally, for W equal to 4, we have 16 times 1 by 16, which is equal to 188 by 48. Therefore, variance of W is equal to 188 by 48 minus square of the expectation of W, which is given by 7 by 4. So this is 7 by 4 whole square. And this difference should be equal to 41 by 48. Next, the value of variance of V. So variance of V is defined as expected value of V square minus expected value of V whole square. So expected value of V square is simply the sum, which is the second moment of V, which is defined as V square times the probability mass function, which is equal to 1 by 4 times the summation of V equal to 1 to 4 of V square, which is given by 1 by 4 into, this is the sum of the first n square values, that is 4 times 5 times 9 by 6. So this is equal to 7.5. And we know that expected value of V, that is the mean of V, is defined as, is equal to, for the given definitions and sum and probability mass function, it is equal to 5 by 2. So we have the variance V is equal to 15 by 2 minus 5 by 2 whole square, which is equal to 5 by 4. Next, we want to find the correlation of W, V. That is, we want to find expected value of W times V, which is equal to, by definition, W, the summation over all values of W and V of the product of W and V with the joint probability mass function. That is P of W, V. Since we do not know the joint probability mass function of WV, instead of calculating this joint probability mass function, we can make use of the already known probability mass function, joint probability mass function of X and Y. So by defining a new random variable U, which is equal to the product W times V, we can find the expected value of U by using the definition of, so the expected value of this random variable U is equal to the summation of the product U times probability mass function of U over all possible values of U. So by this definition, U should be equal to the product of minimum of X comma Y into max of X comma Y. So if you observe the function, by closely examining this function, we can clearly see that this should be equal to the product of X and Y. Since if X is the minimum value among X and Y, then this minimum function should give you the value X, and this maximum function should give you the value Y. So whatever the value of X and Y, whichever is greater, the function U will always equal the product X and Y. Belongs to the range SU, where SU consists of the elements, basically, which are product of these two values of X and Y. So for given X equal to 1 to 4, X equal to 1, 2, 3 and 4, and Y equal to 1, 2, 3 and 4, the product basically consists of the following values, that is 1 times 1, 2, 3, 4. The next one is 6, 8, 9, 12 and 16. So for U equal to 1, we want to find probability of U equal to 1, and probability of U equal to 1, and this probability should be equal to, by definition, sum of the values of the joint probability mass function at which these values of X and Y map to U equal to 1. So the values of X and Y that map to U equal to 1 are X equal to 1 and Y equal to 1. So this should be equal to probability of X equal to 1, comma probability of X equal to 1, comma Y equal to 1, which is 1 by 4. That is from the given joint probability mass function. For U equal to 2, that is probability of U equal to 2 is equal to probability of X equal to 1, y equal to 2 plus probability of x equal to 2, y equal to 1. So both of these points basically correspond to or map to value of u equal to 2. But from the xy plane of the joint probability mass function, we can clearly see that these two values are, for x equal to 2 and y equal to 1, this is 1 by 8. For x equal to 1 and y equal to 2, this is 0. So the sum is still 1 by 8. Similarly, for u equal to 3, probability of u equal to 3 is equal to probability of x equal to 1, y equal to 3 plus probability of x equal to 3, y equal to 1, which is equal to 1 by 12. Similarly, we can calculate the probabilities for all the other values as follows. Probability of u equal to 4 should be equal to 1 by 8 plus 1 by 16, that is equal to 7 by 48. And probability of u equal to 6 is equal to a probability of x equal to 2 and y equal to 3 plus probability of x equal to 3 and y equal to 2, which is equal to 1 by 12. And similarly, for u equal to 8, we have 1 by 16, and finally for u equal to 9 is equal to 1 by 12, and u equal to 12, we have 1 by 16, and u equal to 16, we have 1 by 16. So we can calculate in this process, thus we can calculate the probabilities of different values of u. So from this definition, we can easily calculate the expected value of u, that is for u. So first we construct the table for the probability mass function of u. For u equal to 1, you have probability of u equal to 1 is 1 by 4, and probability of u equal to 2 is 1 by 8. Probability of u equal to 3 is 1 by 12. For 4, we have 7 by 48, and for 6, we have 1 by 12. For 8, we have 1 by 16. For 9, we have 1 by 12. For 12, we have 1 by 16, and for 16, we have 1 by 16. So this table basically gives the definition of probability mass function of u, that is probability mass function of Wv. So we have expected value of Wv is equal to the summation of u times probability mass function of u. So by basically inserting the values from this table, we can easily calculate that the correlation function is equal to 5. By using the values determined so far, we can also calculate the functions such as correlation, such as covariance, by using the definition of covariance, which is difference between the correlation function and the product of individual expectations, and also the correlation coefficient. So in this example, we have learned how to use the definition of the joint probability mass function to calculate the statistics, or to calculate different statistics of different derived discrete random variables. In this case, minimum of x, y and maximum of x, y. Thanks for watching.